Well, hello and welcome back to another episode of Quantitative Bites. It's great to see you all. I hope you're doing well. So today I'd like to continue with the series of videos we're making looking at implementing linear algebra functions in C++. We're slowly building up towards a linear algebra library that we can use to solve all sorts of problems in C++. And what I particularly want to focus on today is vectors. I know this is maybe not going to entirely make sense because, of course, we can represent vectors simply using matrices. A vector is, of course, very simply a matrix with a single column and n number of rows, and we could use the QB matrix 2 class that we've been developing to represent a column vector, as it's called, in that way. And indeed, we did look at some examples of that when we were testing the QB matrix 2 class before. However, there are some specific aspects of vector arithmetic that are really quite unique to vectors, and it wouldn't make sense to take the code for those and to put that into the QB matrix 2 class. So I've decided that it makes a lot more sense to create a separate class specifically to handle vectors. So that's what we're going to talk about today. As with my previous videos, I'm going to give just a very brief introduction to the theory of what we're going to be doing, a little bit of an overview of vector arithmetic, just for those of you who may not be familiar with it, nothing too complicated, and then we're going to move on to actually look at the code and see how I've gone about implementing a vector class in C++. That just leaves me to say before we begin, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try to make a video roughly once a week, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Okay, well, without much further ado, let's dive in and have a look at vectors. Okay, so what we're aiming to do today is to create a simple class that will allow us to implement and handle vectors in C++. So a very basic vector would be something like this. This is the vector A, which is then basically just a column of elements A1, A2 through to AN. And you can see that this is essentially the same as a matrix, but it just has one column and n rows. So as I've just been saying, we could represent vectors simply using the matrix class, but because some specific aspects of vector arithmetic that we want to implement, it makes a lot more sense to do it as a unique class. Okay, as I've written here. So we're going to implement a specific class for vectors. Okay, so the basic operations that we want to implement are the addition of two vectors, subtraction of two vectors, so that's subtraction of one vector by another, multiplication of a vector by a scalar, multiplication of a scalar by a vector. Notice that obviously there's no condition for multiplication of a vector by a vector. That simply wouldn't make any sense. The reason for that you should be able to see if you go back and look at the theory video I did on the matrix arithmetic earlier. We also then want to implement the vector dot product and the vector cross product, and I will introduce what those are briefly in a moment. Okay, so very basic vector arithmetic. If we do we want to consider vector addition, so we have the vector A plus the vector B, and this is going to give us the vector C. So we can represent that in this notation like this. We have our vector A here, elements A1 through to AN, and our vector B with elements B1 through to Bn, and the addition of those two vectors simply gives us the result C, where the elements are A1 plus B1, A2 plus B2 through to AN plus Bn. Very simple. Likewise, vector subtraction, vector A minus vector B equals vector C. We have exactly the same, and here in our result C we just get A1 minus B1, A2 minus B2 through to AN minus Bn. So that's really very basic, so really nothing much to do there. Multiplication by scalar, similarly very simple. The vector A multiplied by the scalar quantity B is going to give us a vector C. So we have our vector here, A1, A2 through to AN multiplied by B, and the result is simply each element of A multiplied by B. So A1B, A2B through to ANB. So again, that's also very simple. Now a little bit more complicated and a little bit more interesting are the vector dot product and the vector cross product. Now at this point I'm not going to go into too much detail about why we might want to use these and what they're for. We will see that when we come to talk about possible applications of these in future videos. But for now, suffice to say that the vector dot product is defined algebraically this way. So the vector A dot B vector b equals c. Okay, notice that c is a scalar quantity, not a vector. And in the previous, as in the notation we had before, we have elements a1 through to an dot the vector b with elements b1 through to bn, and the result of that is simply a1 times b1 plus a2 times b2 through to an times bn. And simply the sum of all of those terms will give us a single scalar quantity, and that is our dot product. Geometrically, the dot product can be defined in this way. So the vector a dot vector b is equal to the magnitude, or the norm of a, multiplied by the norm of b, multiplied by the cosine of theta, where theta is the angle between the two vectors. And that is illustrated in this diagram here. Okay, so if this is our vector a, and this is our vector b, this is our angle theta, then this equation here would give us the dot product of vector a and vector b. Now this also gives some indication of how the dot product can be used. Now obviously we could use the dot product to calculate the angle between two vectors. If we've been given vector a and vector b, you can see that quite clearly we could rearrange this equation in order to extract the cosine theta term, and therefore we could calculate the angle between two vectors. Now that can be incredibly useful, but also we can see that in the case where b is a unit vector, meaning that the magnitude or the length of b is 1, then we can see that this would become the magnitude of a times 1 times cos theta, which is, of course, the magnitude of a times cos theta, or the norm of a times cos theta, which is this term here. And you can see that that then essentially forms the projection of vector a onto vector b. So that applies as long as b is a unit vector, and that also can be very useful. It gives us the ability to project one vector onto another one, and that can be incredibly useful. So finally is to talk about the vector cross product. Now the vector cross product, interestingly enough, is only defined for 3-dimensional and, curiously, 7-dimensional vectors. Now we're not going to concern ourselves with the 7-dimensional case. I'm not really sure that there would be very many practical applications for that, although I'm happy to be proved wrong. But what we are going to focus on is the 3-dimensional case, and we can define the 3-dimensional vector cross product by using what's called the formal determinant. So if you're not sure what the determinant of a matrix is, you can look back at the episode I did on that, the previous video where we looked at calculating the n by n, the determinant of an n by n square matrix. So the formal determinant simply means that we have something like this. So we have our terms I, j, and k here. Now these are vectors, and these simply represent the unit vectors for our basis or coordinate system that we're using. So, this could be say 1 0 0 0 1 0 0 0 1, something like that. So they represent the coordinate system that we're working. You don't need to worry about that too much. And then by vector a, the terms of vector a, a1, a2, and a3, and the terms of vector b, b1, b2, and b3 in orange and blue respectively. So if we put those together like that into a square matrix, then the cross product is defined as the determinant of that square matrix. Now, of course, we can't completely evaluate this because these are vectors, and so that's a bit strange, but we consider just the symbol, so the symbol for vector I, the symbol for vector j, and the symbol for vector k, and that's what we mean by the formal determinant. Okay, and as we saw in the previous video talking about matrix determinants, this is a 3x3 matrix, so we can expand that determinant as being the determinant of this submatrix here, A2, A3, B2, B3, and in the previous video we saw that that's called the minor of the ith term of this term here. So this is this matrix here. So as I say, look back at the previous video if you want to know more about that. And similarly, so that becomes minus the determinant of the minor of the jth element plus the determinant of the minor of the kth element. So we get this, and we can then expand this out. These are just 2x2 matrices, so the determinant is given simply by a2 times b3 minus a3 times b2 times the I unit vector minus and so on. Okay, so we can see how that works, and this gives us this is the equation that we can use to calculate the vector cross product of vector A and vector B. Okay. Now, geometrically, that's actually quite interesting. So what that means is if we take vector A cross vector B, it gives us a new vector, vector C, and the direction of that vector, vector C, will always be perpendicular to the plane containing vectors A and B. So vectors A and B will always lie in some plane, unless, of course, they're exactly parallel. If they are parallel, then the cross product naturally comes out at 0. And vector c will always be perpendicular, so essentially it gives us the normal to the plane containing the vectors a and b. And of course that can be extremely useful. We can use that if we need to calculate the vector that is normal to any other pair of vectors, which, as I say, can be surprisingly useful. Now also the length of vector c is equal to the area of the box contained by vectors b and a. So that's the grey shaded box here. Okay, so that's the length of vector c is equal to that area, which is fairly interesting. Okay, so that's a really basic, really quick overview of vector arithmetic. We're going to look now at the code that I've created to actually implement that in C++, and then we'll have a look at very quickly how we can go about testing that code to make sure that everything works properly. Okay, so this is the code that I've created for the QB vector class. So as before with the QB matrix 2 class, I've done this using templates, and so I've put all of the code into one header file that I've called qbvector.h. And when I talked about how we were going to do the matrix class, I talked about doing that because we're using templates. It's necessary to bring everything into one header file. We can't split between a header file and a CPP file as I would normally like to do. Again, I'm not going to go over that in too much detail right now. In the first first episode in this linear algebra series, I talked about that, so you can go back and check that out. I did go into that in a little bit more detail. Exactly as with any header file, we have our include guards as normal. We include a bunch of stuff that we need. So IOStream, IOmanip we need just for doing nice formatting of any displays we want to generate, standard exception or std exception because we're going to make some exceptions for error conditions, math.h and vector should be fairly obvious. So we use template class T and then class QB vector because, as I say, I'm using templates because I want the user to be able to create vectors of any type, so they can use double precision floating points, single precision floating points, or even integers. I, to be honest, don't really envisage any situation where someone would want to use an integer data type, but it is theoretically possible. But they may want to use single or double precision, and rather than hard coding for a specific data type, I thought it better to use templates. So we set up, in our class definition, we set up our public functions or public methods, starting with the default constructor with no input parameters. We have a constructor that accepts an std vector instance containing our input data of type t, and we have a destructor. And we then have functions to return parameters of the vector, which is the only one we have is to return the number of dimensions, get numdims. Notice that we don't have anything to set the number of dimensions. That's done automatically when we add data to it. The number of elements in this vector is going to be the number of dimensions of our vector class that we're creating. We then have functions to handle elements of the vector. So we have getElement, which simply returns type t and accepts as input int index, being the index of the element we want to retrieve. We're then going to overload the plus, minus, and multiplication operators so we can do those properly. And we have a friend function here to overload the multiplication operator. Okay, so this is for the condition where we have a QB vector class on the right hand side, so this would be scalar times vector. Okay, for the condition where we have vector times scalar, we don't need friend, but we have to do it as friend when we do it the other way round. Okay, and we have a couple of static functions, so these mean that these can be instantiated without reference to a specific instance of the class, which can be extremely useful. And that is how we're going to define the functions for the dot product, which returns a scalar value of type t and accepts as input two matrices A and B. Accepts as input two vectors, QB vector instances of type t called A and B. And we also have another static function for the cross product, which accepts as input again two QB vector instances, but this time returns an instance of the QB vector class of type t. And then in our private section we just have our vector data, which we're storing using an std vector class, an instance of the std vector class, of course, of type t, and we have a variable to store our number of dimensions. That's it for the class definition. It's all pretty straightforward. Now the constructors and the destructor are very simple. So the default constructor simply sets a numdims to 0 and sets up an empty std vector instance for the vector data. The constructor that accepts as input input data of type std vector of type t, simply makes a copy of that using m underscore vector data equals input data, and sets m underscore ndims equal to input data dot size. So that's pretty basic. And the destructor, we're not actually using that for anything at the moment because we're using the vector class from the standard library. It takes care of cleaning up the memory allocations itself, so we don't need to worry about that. We have functions to return parameters. We have a function to return the number of dimensions. That's very simple, just returns m underscore ndims. We have a function to handle elements of the vector. Okay, this is the to get an element, so returns an element, a single scalar of type t corresponding to the element at index given by int index, simply return m underscore vector data index. Really very simple. And then we come to the overloaded operators. So first of all, we overload the plus operator, okay? And first thing we need to do, this is for vector plus vector, and we need to check that the dimensions match, okay? So if the number of dimensions in the left-hand side vector is different to the number of dimensions in the right-hand side vector, then this operation makes no sense. So in that case, we throw a standard exception. I've just used invalid argument for now. In the future, I may change those to specific exception types, but invalid argument should work for everything anyway. And we print with the message there, vector dimensions do not match. We then create a instance of std vector of type t for our result data, and then we're simply going to loop over all of the elements of our pair of vectors and push back into result data the sum of those elements. So we have m underscore vector data dot at I plus right hand side dot m underscore vector data dot at I. So that will take the sum of the ith element and push it back into result data. And then all we have to do is form result from result data. So we have qb vector of type t, result data. So that's using the constructor that accepts as input an instance of the std vector class. Okay, so that gives us a qb vector instance called result, and we simply return that. Okay, that's pretty straightforward. We then have exactly the same thing really for minus, except we've changed the plus to a minus, otherwise it's identical. And multiplication here by the multiplication operator. So this is to perform multiplication of a vector by a scalar. So we're accepting as input a scalar quantity of type t, and we're operating on essentially the vector class that we're in, the instance of the vector class that we're in. And we're going to perform scalar multiplication. We simply have to loop through every element in the vector and multiply it by the scalar quantity given here by RHS. Okay, so we, as before, we create an instance of std vector of type t called result data, and then we simply loop over all of the dimensions and do result data dot pushback m vector data at I to multiply by RHS, and then we construct a new QB vector instance called result based on that result data, and we return that result. So that's really very simple. The last of the overloaded functions here, which is declared as friend, this is for the condition where we have a scalar multiplied by a vector, as opposed to the previous one, which is vector times scalar. This has to be declared as a friend because this function itself cannot be a member of the QB vector class. And you'll notice in the definition here, normally we declare all of these functions as belonging to QB vector, okay, QB vector t colon colon, and this one we do not, but it's declared as friend, which means that it continues to have access to the internal or private members and functions of the QB vector class. So again, we simply do scalar multiplication in exactly the same way that we did in the previous function that I've just described. The only difference is that now we have two input variables. At left-hand side is our scalar quantity, and right-hand side is now our QB vector instance. Okay, so just a little bit of change. We do LHS multiply by RHS dot m underscore vector data dot at I. Notice because we declared this as friend, we can access this private member from the QB vector class. Otherwise, that's exactly the same as the function I've just described. Okay, and then we have our static functions. These implement the dot product and the cross product that we've just talked about. Okay, so we have our dot product function that returns a scalar quantity of type t, belongs to the QB vector class, although, as I say, it's declared static, so we can use it without reference to a specific instance of the class, and it accepts as input two QB vector variables called a and b. Again, as before, the first thing to do is to check that the dimensions of those match. If they don't, it doesn't really make any sense to try to compute the dot product, so don't worry about that. And we then create a variable called cumulative sum of type t, and we set that initially to 0. Notice I'm using static cast to t here, because this number that I've specified here would automatically be a double, and I want to cast it to whatever type t is, whatever type we're using. So I put static cast of type t as 0.0 to set cumulative sum to 0, and then we're simply going to loop over every element in the two vectors, and we're going to calculate the cumulative sum as we go. So if you remember back to the slide, the dot product is simply a1 times b1 plus a2 times b2 and so on. So this is what we're doing, cumulative sum plus equals the element of vector a at I multiplied by the element of vector b at I, and we simply add all of those up as we go and then return cumulative sum, and that's it. That's the vector dot product. And finally, our last static function here to calculate the vector cross product. This returns an instance of QB vector because the vector cross product is itself a vector quantity. It accepts as input two QB vector instances of type A, called A and B, both of type t. As before, we check that the dimensions match. It doesn't make sense to calculate the cross product if it doesn't. We have an additional check to check that the number of dimensions is exactly equal to 3. If it's anything other than 3, then we just throw an error because the cross product can only be computed for 3-dimensional vectors, or, as I said before, 7-dimensional, but we're not going to concern ourselves with that case. And then we calculate the cross product. So we set up a instance of std vector called result data, and then we simply calculate the 3 terms. We know that our vector is 3-dimensional in this case. It has to be, so we don't need to use a loop. We can just do this. And these are simply the terms of the equation that I showed in the slide previously. So you can go back and have a look at that. We just do result data dot push back, and then that's the first term. Okay, so the first element 1 of vector A multiplied by element 2 of vector B minus element 2 of vector A multiplied by element 1 of vector B, and so on. The only important thing to note is this minus sign here. If you look back at the slide from the earlier part of the video, then you can see, should be able to see what's going on there. And then that's it. So that will calculate result data, and then we simply form a result data into a QB vector instance called result, and we return that. And that's it. That is the basic code that we need, or that is all of the code that we need to implement a basic class to handle vectors in C++. So let's have a look now at how we can go about testing that. So this is the code I've created to do the testing, simply called testcode.cpp. It includes a bunch of stuff. Obviously make sure we include qbvector.h we've just been talking about. I'm using namespace std here. I don't normally do that, but simply for the purposes of testing this code, it's quite useful. We have a very simple function to print out a vector. Now for those of you that have seen my videos looking at matrices earlier, you'll recognize this is pretty much the same as the print matrix function that I wrote before, except of course we only loop over the rows. We don't need to loop over the columns as well. So it's pretty, actually, let's just put a tab in there for neatness. Okay, so this is where we use the IO manip functions here for std fixed and std set precision 3, so it will print them out to 3 decimal places, which just keeps everything looking neat. And then we have in our main function here, we test that we can create an instance of the vector class. We set up an std vector instance called testdata1 containing the values 1, 2, and 3, and then we put that into, we create an instance of QB vector of type double called testvector1 using that test data, and then we use print vector to display that. And then we test the basic arithmetic with vector plus vector, so we create a second vector there, and we test the result of adding vector 1 and vector 2 here. So we do test vector 3 equals test vector 1 plus test vector 2, and we display that. And then we do test vector 2 minus test vector 1, as you can see there, and we display that. Test vector 1 multiplied by 2, and display that there, and 2 times test vector 1 and display that there. And then we test the static functions. We test the dot product dot product of test vector 1 and test vector 2, like so. Okay, which gives, okay, so we simply do double dot product, because the dot product is a scalar quantity. Now it's equal to QB vector of type double colon colon. Because dot was a static function, we can instantiate it without referring to a specific instance of the QB vector class, and this is an example of why that could be very powerful. And then we simply display the dot product, and then we test the cross product in exactly the same way, and we define a new test vector which is not parallel. So test vector 1 and test vector 2 are parallel, so the cross product there should be 0, and we define a new test vector which is not parallel to those, which is test vector 5, and we test the cross product of, I've written cross produce there as well, and we test the cross product of test vector 1 and test vector 5 and have a look at that. And then we look also for completeness at the dot product of test vector 1 and test vector 5. Okay, so that is all the code I've written to do the testing. So let's just save that because I made some minor changes. If I go to my terminal window, we can compile that as G++ -o testcode.cpp -std equals C++17. Let's just compile that. And if we run our code, then we get all of the results. So we see, so from here at the beginning, we create an initial instance of the class with data, test vector 1, it's 1, 2, 3, and then we're going to test vector 1 plus the vector 2, 4, 6, which gives, of course, 3, 6, 9, which is the right result. Test vector 2 minus test vector 1 gives 1, 2, 3, as we would expect. Test vector 1 times 2 is 2, 4, 6. 2 times test vector 1 is the same, 2, 4, 6. The dot product of test vector 1 and test vector 2 is 28. I've checked that with other software, that is the right answer. The cross product of test vector 1 and test vector 2 is 0, 0, 0. And we then define a new test vector which is not parallel to test vector 1, which is going to be -1, 5, -3.2. And we'd compute the cross product of test vector 1 and test vector 5, which is this, -21.4, 0.27. Again, I've checked those in other software, they are correct. And the dot product of test vector 1 and test vector 5, which gives -0.6. And I've tested, as I say, all of those with other software, and I believe that those are indeed the right answers. Okay, so there we go. That's everything that we need to do to implement a simple class to handle vectors in C++, which we're going to use as part of our linear algebra C++ library that we're developing. Okay, so in the next video I'm going to focus on how we can extend this a bit further to a little bit more functionality, but otherwise that's everything I really wanted to talk about today. So thank you very much for watching. I really hope you've enjoyed the video. If you have, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Anyway, listen, it's been a pleasure. I really look forward to seeing you in the next video next week. Thank you very much for watching. Bye.